Thank you, Julie. Last year when I presented here, I opened the presentation by saying I'm from EPA and I'm here to help you. And when I do that for non-EPA audiences, this is usually the response that I get. The idea was last year I wanted to take the information that I've gleaned here at the meeting back to the agency to try to create and broaden our knowledge and create a community of remote sensing users within EPA. So this year, while I'm here, I'd like to say I'm still at EPA, but what I'd like to do is thank you for helping me, because taking the shuttle, the HICO data from station, we've been able to create some products that I'd like to show you during my presentation that are of great use to the agency. One of the first things I want to show on this first slide is the amount of effort that went involved in putting together our research program. We had personnel that were involved from EPA, from 2 national laboratories within the Office of Research and Development, as well as from the Navy, the Naval Research Laboratory, Stennis Space Center. And there were about 15 folks that are listed on the slide from all 3 organizations. So this was truly one of those intergovernmental, inter-EPA cooperative research efforts. Now, okay. It's EPA's mandate to protect human health and the environment, and we tried to do in our program here, we tried to come up with an innovative and sustainable solution for addressing several of the nation's environmental problems. The HICO instrument offers the agency and the environmental community an unprecedented opportunity to observe changes in coastal and estuarine water quality across a range of spatial scales, which is just not possible with a field-based monitoring program. Throughout my talk, there will be a couple of terms that I'll continually use, and I want to define them now. One is I'll refer to ocean or estuary color, and the other is remotely sensed reflectance. So what is ocean color, estuary color? Well, if you can relate back to probably your 8th or 9th grade science class, it's looking at using data from the visible part of the spectrum, from the Roy G. Biv part of the spectrum, to determine what is the remotely sensed reflectance from that part of the spectrum. And the reflectance is basically, it's a ratio of water leaving radiance from the water surface to that which is downwelling from the sun. So after having had this brief Ocean Optics 101 class, let me tell you about our program objectives were to use the HICO imagery to develop what we considered a novel space-based environmental monitoring system that provided information for the sustainable management of coastal ecosystems, and then to demonstrate that water quality information derived from HICO could be incorporated into a prototype smartphone application to disseminate data to managers within the EPA Office of Water. And our hope was that with water quality news reports, that the public would then change the social and economic dynamics of the nation to be aware not only of its water quality conditions, but to support those practices that could maintain or improve conditions at your favorite recreational area. So the hope was that we could take this information, and as many of you did, as I did this morning, go to the Weather Channel or some appropriate cable outlet and pull up, see what the water quality conditions are at your favorite beach. Or if you had your smartphone, click your app, go to your favorite beach and decide, is this going to be a beach day based on what the water quality is or not. So we want to make water quality and environmental monitoring part of the everyday vernacular of the general public. So let me give you a little bit of history about the imager and its intent. HICO, from a paper that Luck et al. Wrote in 2011, HICO was intended to be a pathfinder for follow-on sensors that would be designed for better resolution and for routine observations of the coastal, riverine, and estuarine waters. And HICO is built on a legacy from the National Research Laboratory PHILS program, which is a portable hyperspectral imager for low-light spectroscopy, and which was flown on several aircraft before the instrument was selected to fly on the space station in January 2007. In 2008, the Ocean PHILS instrument, or the young HICO, began its reconstruction following a critical design review within the Navy. And in September 2008, it was space qualified and delivered to the Department of Defense Space Test Program for integration and spacecraft level testing. In April 2009, the instrument was shipped to JAXA for launch. And later that year, in the fall of 2009, HICO was launched on a JAXA H-2 transfer vehicle. And by late September, about 2 weeks later, HICO was installed on the International Space Station in the Japanese Module Exposed Facility. This is the slide on your right is HICO. HICO stands for Hyperspectral Imager for the Coastal Ocean. It's the first spaceborne imaging spectrophotometer specifically made to monitor and to characterize the coastal ocean from space. Like I said, it's been installed on the Japanese experiment module, and it's part of the HICO RAID's payload. On the two images on my left, the top one in the upper left-hand corner is the HICO RAID's experiment payload as it's attached with a robotic arm to the Japanese experiment module. And the one below that is a picture of, in the red circle, is HICO covered up, and it's a protective foil. If we go back to the larger image, HICO consists basically of two parts. It has a spectrometer, which gives us the spectral information, and it has a camera, which allows it to take hyperspectral imagery and photo. HICO is what's called it's a whisk broom sensor, and as you go along the flight orbit, it scans back and forth in this fashion, and then that information is then stored on computer. The ruler that's there is a 20-inch ruler, so HICO is literally about the size of the speaker podium here. In terms of its technical specifications, I've listed several under the parameters and the performance. Its spectral range, it goes from the ultraviolet to the near and to the infrared. The bandwidth is at just under 6 nanometers per band, so it's a very fine resolution. About 100 channels. There's some technical, it has a high signal to noise ratio. And the important thing from a monitoring and an ocean color perspective is the ground resolution at nadir, which is 100 meters, which makes HICO one of the highest resolution of the ocean color sensors that are available for environmental monitoring. The European Space Agency has a 300-meter resolution image spectrometer on Maris, and then MODIS, which is a NASA spectrometer, has about a 1 kilometer resolution. So HICO is a very high resolution, and for scene size, as it's doing its whisk broom sensing, it can scan 50 kilometers by 200 kilometers with each pass. So it's a very wide, high resolution swath, and which is large enough to capture the scale of coastal dynamics, but yet small enough to get the resolution for features that happen within estuaries, small estuaries. In our program, we collected 49 images from 4 estuaries along the Florida Panhandle from April 2010 to May 2012 during station expeditions 24 through 31. In the upper left is the red box is the part of the Florida Panhandle where we collect our imagery from, and we collected imagery from Pensacola Bay, Chockahatchee Bay, St. Andrew Bay, and St. Joseph Bay. And from an oceanographic characterization perspective, Pensacola, Chockahatchee, and St. Andrew Bays are shallow microtidal estuaries that are brackish water, which means they get salt water from the Gulf of Mexico mixes with fresh water from rivers and streams on the land and from the watersheds. But St. Joseph's Bay is a little bit unique in that it's slightly deeper. It's about 8 meters difference, and it's not influenced at all by the inflow of fresh water. An extensive part of our program was field validation, because our goal here was to create algorithms for a select few water quality parameters that the agency measures, and to validate those algorithms. That was using the HICO data, and then to validate those algorithms with a field program. Here's a distribution of field stations in Pensacola, St. Joseph, St. Andrew, and Chockahatchee Bay, and there was about 80 field stations that were occupied in total. The green dots are those stations that were water quality moorings in that they had instrumentation on them that measured chlorophyll content, turbidity, water clarity, and the absorption of light due to color dissolved organic matter, which is known as CDOM. The yellow stations were the stations where we collected above water radiance, the remotely sensed reflectance data, temperature, salinity, as well as some other optical properties within the water column. And the red stations were the same as our yellow stations, but we actually collected discrete water samples, which were then analyzed within the laboratory. As part of the field validation program, I just wanted to show you the instrumentation that we're involved. We did water column profiling, the above water radiometry, which consisted of 2 radiometers, one looking at the sky, one looking at the sea surface, and then we had laboratory analyses. These were samples that were collected from a small boat, so we had crews that were on the water within 1 to 3 days of a station overflight. And part 2 was we tried also to incorporate autonomous underwater vehicles into the program. The Stennis Space Center Naval Research Lab deployed a Slocum electric glider off of Pensacola Bay that flew between the 15 and 30 meter contours and collected temperature and salinity, chlorophyll, and CDOM data. And then inshore, we had a team from my lab in Narragansett in Rhode Island that deployed a REMUS, a remote environment monitoring unit, in Pensacola and Chockahatchee Bays, and also collected temperature, salinity, chlorophyll, and turbidity at about a 1 meter depth. And again, with the huge field validation program that we had in place, we were able to then see if we could validate the models that we had created. Now, before we get into processing of HICO data, there's another part of our ocean optics class I'd like to bring up, and that is what are the optical components that affect a coastal image. When light leaves the sun and enters the atmosphere of the Earth, light it's scattered and absorbed on multiple pathways. In fact, and I guess the statistics kind of go like, if for every 100 photons that enter the atmosphere from the sun, only about 40 actually make it to the Earth's surface. And then if you have to then migrate those photons through the water column off of the seabed and back out of the water column up to a sensor, which either could be a radiometer on a space-based platform or it could be your eye, then it's it gets to somewhere between 10 and 25 photons. So we're looking at low levels of light that are reaching the sensor in order to process the data. And that scattering can be due to a variety of things: the atmosphere, aerosols, the water surface, suspended particles, absorption, again, atmospheric effects. And all of these, in order to get that one signal out of the water that represents the light coming out of the water, have to be removed. When we processed our HICO image, we had an 11-step process that involved, initially, we would make a request to Oregon State University, which was the contractor that initially processed HICO imagery to an uncorrected data set, atmospherically corrected data set. So you would receive the data. We would then go through the process of recovering the true at-sensor radiance values, removing sun glint. Sun glint can happen as you're driving along the highway and you get a glint off of someone's windshield. That flash of bright contains no spectral information. So for those pixels that were sun glint affected, they had to be removed. And then we did our atmospheric correction using a process called offshore pixel extraction. We initially tried processing the HICO data using traditional atmospheric correction programs, and we were not successful. We don't know if it was due to the characteristics of one of the HICO sensor itself in like the blue-green range part, or also because HICO is so new, a lot of the commercially available atmospheric programs don't have the characteristics of the sensor as part of their package. So we tried using a generic hyperspectral sensor, and it didn't work out. So what the offshore pixel subtraction process was, we would find a pixel offshore that was less bright than that which was in the estuary, and then subtract the two from one another. The theory being that the atmospheric effects offshore are the same effects as those onshore, and then through subtraction you are to a first order removing the atmosphere. Then we would take the middle steps 4 through 7 were conversion. We were converting our radiance data now to remotely sensed reflectance data, and then we had to, because we get an image swath from the station, we had to then create and we had to clip our estuaries from that image with the remotely sensed reflectance for that particular body. And then we did all our data processing in Excel. And from the models that we created, we then processed all 49 of those images for turbidity, CDOM, total suspended matter, and chlorophyll. And then today I'll show you 3 of the 4 models that we came up with. This is just an example of some of the processing steps that were involved. First, on the far right is a HICO image of Pensacola Bay, and in the yellow box is Pensacola Bay itself. And within Pensacola Bay, we pulled out a pixel that initially, which is the step 1, which was the level 1, what's called level 1B calibrated radiance, not atmospherically corrected. And then the next one is a step 4, where we've actually gone through the process of removing the atmospheric effects. And one of the things you'll notice in that particular, the spectral shape has changed, and what you see now is what's called the classic shape for coastal and estuarine waters. It's depressed in the blue and the green because of the absorptive effects of CDOM, color dissolved organic matter, which is a major absorber of light in that particular region. The spectral peak at around 55 nanometers is due to suspended material in the water. And then off as you go into the red and the near infrared parts of the spectrum, you will see there are some other humps, if you will. One which are a secondary absorption peak for chlorophyll, which then allows us to then pull out that signal, as well as some other spectral peaks that are associated with other pigments in the water column. And then finally, in the lower the lower right, we converted that information into remotely sensed reflectance, and then once we have that signal, then we would compare what we processed with what was actually measured off the water. And that would be in the slide with the yellow background. In that slide, we've taken data from a station in Pensacola Bay, and we've overlain the above water radiance data on top of the HICO atmospherically corrected data. And you can see that there is close correspondence, and it does assume the shape of the characteristic shape for case 2 waters. So that's when we knew we were on track. And for this slide shows we did an example from 3 other stations in Pensacola Bay, where the red line is the above water radiance and conversion to remotely sensed reflectance in comparison to the HICO atmospherically corrected spectral data at that location on that date. And you see again, there's correspondence and there's a general fit between the 2 types of data. So with that, we were pretty pleased that the offshore pixel subtraction program did indeed achieve the atmospheric correction that we needed. So having an atmospherically corrected data set that we could work with, we were then able to marry the in-water program with the HICO program to develop several research models. And the first one I want to show you here is the chlorophyll model. And the question is, well, what's the importance of chlorophyll? And from an environmental monitoring perspective, it's an indicator of phytoplankton abundance, as well as an eutrophication in an estuarine system. Usually high phytoplankton concentrations is a good indicator that a system could be moving into a eutrophic arena. So in the far right top slide, we used an approach of Gielsen et al. In 2011 to look at 3 bands in the near-infrared part and the red part of the spectrum to develop a regression between the bands and laboratory measured chlorophyll. And the R-square for that relationship is pretty good, 0.68. Then the model that was the result of that regression, which is located under the image here, we then used that model to process all the HICO images. But let me just point out that the slide below, and it'd be the far right lower slide, we actually then said, okay, with the model, how well does it measure up when compared with measured concentrations? And the regression there, the R-square was 0.82, so it's a pretty good regression. And we were able to come up with an error of about 1.7 micrograms per liter, which on a grand scheme of things is not bad. In estuaries such as along the Gulf Coast, where there's not a whole lot of chlorophyll, that's kind of a big error, because in some of those estuaries you're only talking like 2 to 3 micrograms per liter. So it's not a bad relationship. The model is a strong model, and it does show, as you can see in the image from Choctawhatchee Bay from October to 31st in 2011, you can get a sense for the distribution of chlorophyll in an estuary, as well as not only along the main stem of the estuary, but actually up into the creeks and rivers that feed the estuary, which are, the red notates the high concentrations up estuary, the green notates the lower concentrations of chlorophyll. Turbidity, what is turbidity? It's an indicator for us that of the total distribution of suspended matter in the estuaries. Again, using models and approach from the literature, we used Chen et al. 2007 to create a model which is located under the image, and then we compared it with turbidity measurements made during one of our profiling packages at all the stations of the 4 estuaries. And we've come up with a model that the R-square is 0.67. The error is just over a half a turbidity unit, which is not bad. So now we can then take that model, apply it to this estuary, and look at what's the distribution of water clarity on this particular image, which comes from, this is in spring of March in 2011. The green notates clear water. The red notates where turbid waters are. And it matches up. The red water, the red pixels tend to match up where you have streams coming into an area. And the clear or the green pixels match up where along the main stem of St. Andrews Bay. And color dissolved organic matter, it's an indicator of light attenuation in estuaries. And the value is, if you were trying to recolonize seagrass in an estuary, you would not want to put it in an area where the CDOM is absorbing all the light in the water, therefore defeating the purpose of putting your eelgrass out. So what we did was we then used an approach for Bowers in 2004 and looked again in the red and near infrared parts of the spectrum, did a ratio against measured CDOM absorption. And in Europe it's called Gilvan. So the European literature with the G, which then explains why the A and the G. So absorption due to Gilvan at 412 nanometers. Our model, the R-square is 0.93, and the error is very low at 0.21 per mil of absorption. This is Pensacola Bay, and the red indicates areas of high absorption within the bay, and there's a unique relationship between freshwater and CDOM. So usually high CDOM is associated with low salinity. So in this instance, you could be looking at the influx or the influence of fresh water into parts of Pensacola Bay. And what we did a comparison between the HICO image and MODIS. The larger rectangular image is a MODIS image that was collected 7 minutes before HICO went over in October 2011. The red box represents the area of the HICO scene. Within that red box is a smaller blue box, which contains pixels that were common to both MODIS and HICO, as well as an area where we had the NRL glider at the same time. What we can see is, if you look at the lower left slide, is a comparison between above water radiometry and HICO data selected from the same wavelengths as MODIS. We then took that information and we put it into, which is called the OC3 chlorophyll model, Ocean Color 3, the NASA model. And what we found is that HICO data, when you plot the results of HICO versus MODIS chlorophyll, there's a good relationship. The adjusted R-square is 0.83, which then says, we can move beyond having regressions for specific estuaries to using a generalized model for estimating chlorophyll in the coastal ocean that can be processed using NASA algorithms. So in kind of a program summary, we use the atmospherically corrected HICO imagery, and with a comprehensive field program, we develop regionally tuned algorithms that, for chlorophyll A, CDOM, and turbidity for 4 estuaries in the Florida Panhandle for just about a 2-year period. And then we took that information and then we uploaded it to an EPA, an internal site, for review and use by the EPA Office of Water, and we've developed a prototype mobile application. The image that's on the slide here, if you look very closely, it says cyanobacteria monitoring. We're going into a next step. And what we would like to do is then take this hyperspectral information and then create an app for an iPhone application, so that then one can also, in addition to looking at water quality, can pull up what's the cyanobacteria distribution at your favorite lake or freshwater pond. And so now we're moving into the world of human health. Cyanobacteria, also known as blue-green algae, usually are inert organisms, but in some instances they can become toxic. And when they are toxic, they can be fatal to some animals. And for humans, they have been, you can get a skin irritation, or there are some gastrointestinal irritations that can happen if you swallow the water. So now what we're trying to do is move to that area where we can go into human health to get information to the states so that they can start to monitor closures in your favorite recreational area. So in conclusion, HICO really helped us to show that it's possible for a hyperspectral space-based sensor to produce products that met the needs of the agency. And it has tremendous benefits, tremendous potential benefits. But there are a few issues that have to be resolved before we can make HICO part of a routine monitoring program. HICO, one of them, HICO is currently limited to only one image per orbit, which if you're trying to monitor East Coast, Gulf Coast, or on multiple estuary areas, it makes it pretty hard to do. And also, because overpass times are really difficult to predict, it's hard to plan a field program based on an overflight. We had our field crews all wound up to go out 1 to 3 days after an overflight, scheduled overflight. Then we'd have to stand down and wait about a month for another. So that's something that, in order for it to become a routine, go into operational mode, will have to be addressed. But still, we consider it to be a very valuable monitoring tool, and we really suggest that since it is a pathfinder itself, it could be transitioned to a constellation of sensors that some of them have been presented this morning. So thank you.
Thank you very much, Darryl. And I think with these kinds of applications that were developed with the small amount of data available through the Naval Research Laboratory, it pleases me greatly on behalf of both the ISS program and the Earth Sciences Division of the Science Mission Directorate to announce to everyone that the program and the Science Mission Directorate are taking over the support of operations and opening up the HICO facility to the entire scientific community. So those who've responded in the past or in the future to the CASIS hyperspectral call for information will have access to tasking this instrument. Other government agencies like the EPA continue to have access in the Naval Research Lab. And then the entire community of the Science Mission Directorate funded users in the ocean color community also have the opportunity to task this instrument. That was just announced on July 11th. Goddard Space Flight Center, the ocean color team there, is reprocessing all the historical data with new and improved atmospheric corrections, and the entire data archive will also be available on the Ocean Color website in a few weeks. And the CDAS system for ocean color analysis is being updated with algorithms so that the whole community can access that. And so we're really excited about this opening up of HICO data to the entire community.